Okay, so we are on to interpreting the correlation results. If there's one thing that you should remember from from these lectures is this, is that correlation is not causation. Let's write that big. Correlation is not causation. If you see that two variables are correlated and you think that there is a causal correlation, and then you find a really nice correlation, a really strong correlation, let's say that you're looking at plant age, you're looking at trees and you're saying, oh, here's age and here's number of flowers. And what you find is this, is that you find a really beautiful correlation. This is as good a correlation as you can possibly hope to find, right? It's a perfect, this is an r squared of 1. It is perfect. As you get a little bit older, you get a few more flowers. It is a perfect correlation. This does not mean that age causes trees to have more flowers. It does not cause it. However much you'd like to believe it, and however much there's reason to believe it, there is still there's a possibility of what are called lurking variables. So maybe, in fact, it's not age that causes a tree to have more flowers, but maybe it's size. And so it's not age that's a causation, but it's in fact size. It's just that age and size are also perfectly correlated. But if you were to find a tree that were old but small, it would have very few flowers. Like maybe it had been blown down by wind, right? But then the size would still fit this because the size is a causal relationship. So you need to be really careful that just because you find a nice correlation, you cannot assume that it's causation. The only way that you can definitively say that you have a causal relationship is that something causes another thing to happen is if you do a very well controlled experiment. Right? That is the only way that you can tell causation from correlation. And how do we do that? Right? So we're going to talk about experiments in the future, but let's think about some research projects that are happening here in ICNART and how we might mistake correlation for causation. So one is that Wiana is looking at the effects of marmots on small mammal colonies, right? Or the effects of marmot colonies on small mammal communities. And so what we can do is that what she's doing, right, is that she's measuring small mammals on areas with marmots and on old marmot sites and then without marmots. And maybe she'll find a really strong relationship between marmots and the density of some small mammal, of let's say hamsters, right? But that does not mean that marmots cause there to be more hamsters. Maybe there's something about marmot colonies, like maybe marmots happen to choose or like to choose sites with a lot of nitrogen on it. And it's that, in fact, it's the extra nitrogen that causes there to be a lot of hamsters. It has nothing to do with the marmots themselves. It's just that marmot colonies are very well correlated with nitrogen. So how do you get around this? So you can do an experiment. If you really want to find out how marmots affect small mammals, what we want to do is an experiment. So we want to manipulate marmots. So one way to do that, one unethical way to do that, is we can kill all the marmots in a colony and see what happens to the small mammals. That's not a very ethical way to do it. So a better way to do it, right, would be if we introduce marmots to an area and we measure small mammals before we have the marmots there, and we measure it for several years before we have marmots, and then we bring in marmots, and now we introduce marmots, and now we look at small mammals, like we look at the hamster densities, and we also have a control site where we don't introduce marmots, and then we can see if there's a difference between the control site and between the before-after of the marmot introduction. Right. So the only true way to get causation is to do an experiment. Of course, experiments are sometimes oftentimes in ecology not feasible, right? It's hard to introduce marmots. You have to find marmots from somewhere, you have to get permits, you have to move them, you have to introduce them, you have to collect data from many years before and after, but these are not easy things to do. So oftentimes what we have to rely on in ecology are what's called natural experiments. So what can you do? If you want to find causation, but you can't actually do a manipulation. Even though you would like to, you just can't do it. What we can do is we can rely on natural experiments, which are essentially if we maybe have areas. So one way to do it is if maybe you go to an area and you measure, for the marmot example, and you measure small mammals, and then somebody else has come and he's killed all the marmots, right? And you can then measure, if that happens during your study, you can do that. You can do it before or after. That's of course fairly unlikely to happen, but maybe you can compare an area where marmots have just very recently been removed, or right where they're expanding. Maybe there's somewhere where marmots are expanding the range, and so the population of marmots is growing. So you find, oh, I'm going to take an area right at the edge of their expansion where I think that right now there are no marmots, but maybe in 2 years there will be marmots. So you can use that natural experiment, right? Right now there are no marmots, but marmots elsewhere are expanding, and so now we're getting more marmots. So you can use natural experiments to mimic true manipulations. Now natural experiments are not as good as true manipulations, but they're often in ecology the best that we can get. So the other way that you can do this, right, is that you can test, or you think that you have some lurking variable. For example, you have trees where you said the age was related to number of flowers, but maybe somebody says, well, I think it's actually size, not age. Well, what you can do is you can measure size and see what the relationship between size and number of flowers is. And then, so essentially you can test alternate hypotheses, right? You can test, oh, well, I have these other lurking variables, but I'm going to test them and see if I get a relationship. And maybe if you don't find relationships with those, you can say, well, it's not these other lurking variables, and so it's more likely that it's my variable that I think that it is. And you can essentially, by process of elimination, measure a lot of things, and then either say, oh, these are things that do have an effect, or you can say, oh, these definitely do not have an effect because I measured them. That's still not as good as an experiment, but it's often the best we can do. Okay, the other thing that we need to be aware of is that we have what's called a restricted range problem. So this is a restricted range. So let's say that you are interested in determining the effect of rainfall, so precipitation, on plant growth. And here is plant growth. And maybe you find a relationship that goes like this. Alright, so you go to maybe many different areas of Mongolia where there's different precipitation, and you've picked some plant species, some tree maybe, or whatever it is that you've chosen, and you measure their growth. And you can say, oh, in these different areas of precipitation, I find this nice relationship. Right? But you have a restricted range problem because you haven't captured all the range of precipitation. Right? So maybe, this relationship might hold here for this level of precipitation, but maybe if you could find some really, really wet area out here, the relationship would actually change. Right? So maybe out here, the relationship would actually be this way, if you could measure it, because here water is limiting, and so the more rainfall you get, the more plant growth you get. But out here, rainfall is no longer limiting. So this plant has all the rain it needs, and so it doesn't matter if you add more rain because it's not rain limited. It's maybe nitrogen limited, or maybe phosphorus limited, or it's limited by something else that's not rain. And so, but if you don't have these data, if you just can't get precipitation out here, then you're going to say, oh, well, I have precipitation and it looks like this relationship, right? Oh, the more rainfall I get, the more plant growth. When in fact, right, once you get out here, let's say, it would actually go like this. So this is a restricted range problem where you don't have a complete set of data, and that means that the relationship might actually change over different range of variables. And so the last thing, though, that we're going to talk about is a couple of things. So, and that is that you have to be really careful when you're using correlations. You have to be careful in how you have to interpret them. Correlations are a tool just to describe your data, but what that actually means, you have to decide, right? The correlation is just a number. Regression is just a number. It's not. It doesn't tell you what the causal relationships are, and it doesn't tell you about other things that could be affecting it. And it doesn't tell you about the real significance of it. So, for example, in fact, I'm going to stop there and then go on with this in a second.